Topics covered in continuity and differentiability. Welcome to the chapter on continuity and differentiability. These two concepts form the bedrock of calculus, providing the essential mathematical framework we need to analyze how functions behave and, more importantly, how they change. Essentially, we are moving from the world of static algebraic expressions to the study of dynamic rates of change. This allows us to describe the world not just as a series of still snapshots, but as a continuous flow of motion and evolution. Throughout this chapter, we will focus on 4 key learning objectives. First, we will explore continuity, where we define the conditions that make a function unbroken and learn to identify points where that continuity fails. Second, we will dive into differentiability to understand the derivative as a measure of the instantaneous rate of change. As we progress, we will master advanced differentiation techniques, specifically focusing on exponential and logarithmic functions, as well as the method of logarithmic differentiation. Finally, we will cover parametric and higher-order derivatives, which will allow us to analyze more complex functions and understand concepts like curvature and acceleration. Once we have established these theoretical foundations, we will examine how these tools are applied in real-world scenarios across various scientific fields. Real-world applications of continuity and differentiability. Now that we have an overview of the topics we will cover, let us discuss why these concepts are so vital in the real world. Continuity and differentiability are far more than just theoretical exercises. They are indispensable tools used across a wide range of professional disciplines. For instance, in physics and engineering, these principles are the foundation of kinematics. If a position function is continuous and differentiable, its first derivative represents velocity, and its second derivative represents acceleration. These calculations are essential for ensuring the structural integrity of bridges and the aerodynamics of aircraft. In the realm of economics and finance, differentiability is used to calculate marginal values. For example, marginal cost or marginal revenue represents the rate of change of total cost or revenue with respect to the number of units produced. Similarly, in biology and medicine, these mathematical tools allow scientists to model the growth rate of populations, track the spread of epidemics, and determine the rate at which a drug is metabolized in the bloodstream. Finally, in the modern field of data science and artificial intelligence, derivatives are the engine behind gradient descent. This is a process used to minimize error functions and optimize the performance of AI models. By mastering this chapter, you will gain the ability to quantify change, enabling you to predict future trends and optimize complex systems in any field involving quantitative analysis.